Yeah. Good morning, everyone. Thank you, Keil, for the kind introduction and for inviting me, for allowing me to share my research here at the University of Warsaw. Let me first introduce myself and the University of Innsbruck. Most of you might know, Innsbruck is located in the west of Austria, in the middle of the Alps. So it's one of these places where you can study or work and hike to a 2,000-meter high mountain. Gregor Weiss, just work with this laser pointer. There's a bit of a lag. Okay, there it works, headed by Gregor Weiss, the group leader. Our group works with develops certain types of single photon sources, quantum dot photon sources, down conversion photon sources, either in semiconductor waveguides or in bulk crystals. And then we apply these single photons for a variety of applications, some more on the fundamental side, doing some interferometry, working out fundamental principles of interference or of quantum physics. For quantum communication, we have a space QKD project, or for quantum metrology, for example, for range finding or for Frenzen interference. And in that group, I lead a team, and my team focuses on three, let's say, different directions. One is on the foundations of quantum physics, investigating fundamental postulates of quantum physics with single photon interferometry. Like the biggest part of the team works on aspects of multi-particle interference, which I will tell you a lot more about today. And recently I have a joint project together with Michael Karpinski on quantum interfaces, where the goal is to develop efficient interfaces between quantum dot photon sources and parametric down conversion photon sources. I will not talk about the first topic today. For those of you who have been around a long time ago, I have given a talk on that topic 6 years ago in that seminar, or in the precursor of that seminar. For those who haven't been around, these publications can give you an intro to this topic. And most of the talk I will spend on this multi-particle interference research. I will give a basic introduction to the topic, introduce so-called suppression laws, which are some analytic rules to predict the dynamics of multi-particle interference scenarios. And then I will concentrate on 3 experiments we did in our team. One relates symmetries with indistinguishability of particles. One is a multi-particle interference experiment with a collective phase. And the final experiment is a time-to-space demultiplexer, where the goal was to convert a temporal stream of quantum dot emitted photons into spatially demultiplexed photons. But let's get started with this multi-particle interference topic. As you might know, photonic quantum computation is kind of a hot topic. There are different strategies how researchers, companies, universities follow this path. Some years ago, there was this kind of breakthrough result published about Gaussian boson sampling being the first photonic system solving a task which is unsolvable on a classical computer. Or which, in other words, was the first photonic quantum computer reaching quantum advantage. And more recently, we have heard several news from PsiQuantum, who showed their kind of chip-based architecture for fusion-based quantum computation, with the long-term goal to build a universal photonic quantum computer. And both these platforms ultimately rely on multi-photon interference. So I think it's a good motivation to understand multi-photon interference and look at its working principles. And to understand it, we have to start very basically with photons hitting a beam splitter. As you might know, photons, as the quanta of light, when they hit a beam splitter, they just have a certain probability to be reflected or transmitted off the beam splitter. And if it's a balanced beam splitter, it will be a equal probability of 1/2. So an incoming photon could either be reflected at the beam splitter or transmitted at the beam splitter, leaving the photon in a superposition state of the two output modes. When you enter the beam splitter from the other side, basically the same happens, except that there's a phase difference between these two between these two directions, which arises essentially from energy conservation. Yeah? The beam splitter needs to conserve energy. This imposes certain relations on the reflection and transmission coefficients, and that ultimately leads to this phase difference of pi here. One can write it down formally as a so-called also unitary matrix, yeah, which relates these input and output modes with this transformation here. And in quantum information, this is known as the Hadamard gate, which describes the transition probability amplitudes between the input and output modes of a beam splitter. Now, if we have two identical photons impinging a beam splitter, like one photon from either side of the beam splitter, and we measure how often do these photons appear as a coincidence, so appear separately at the two outputs of a beam splitter. And if these photons are indistinguishable, that means they're really the same, yeah, in their color, in their polarization, and so on. One has to add the probability amplitudes, not the probabilities, yeah, to work out what is the probability for this coincidence. And there are like two possibilities. Both photons could be in the spar state, yeah, so they stay on their respective side of the beam splitter, or both photons cross the beam splitter. And these two events are intrinsically indistinguishable. So one has to add up the probability amplitudes, and these probability amplitudes correspond either to the on-diagonal elements of this unitary matrix, which I colored here in green, or the off-diagonal elements of this matrix, which I colored here in blue. And due to this pi phase difference, these two amplitudes just cancel out destructively, and there is zero probability of such a coincidence. So in other words, the photons never make it to this coincidence state, but they always appear together on one of the two sides. Yeah? And this is known since the late 80s, and it's known as the Hongo-Mandel effect. And that's the very basic of this multi-photon interference, which I will talk about more today. Maybe one important comment here. So indistinguishability means that there is no additional degree of freedom besides these spatial modes here of the beam splitter, which allows a discrimination of these two transition amplitudes. Yeah? And no additional degree of freedom means they should be the same in their spatial mode profile, they should temporally overlap, should have identical spectra and polarization. And all these degrees of freedom are typically then called internal degrees of freedom in the community. Yeah? In practice, of course, this is never exactly perfect, yeah. So there's always some finite distinguishability of these internal modes, and how indistinguishable they are. This can be measured in the so-called Hongo-Mandel dip. So one tunes one of these internal degrees of freedom on purpose. Typically, it's done via time, so just delaying one of the two photons in time, and then measuring the coincidences as a function of this time delay. This then typically leads to this dip, yeah, where at this plateau the photons are distinguishable, so the wave packets don't overlap in time, and I just get an output probability of 1/2 for these coincidences. And in the center of this dip, there's maximum overlap. Then they should ideally be perfectly indistinguishable, and I should drop to 0. And in reality, I drop to a little more than 0. Yeah, and this depth of this dip is then the visibility of this interference, and that's a direct measure of the indistinguishability of the photons. Now, multi-particle interference is, before I come to that, so one, especially matching this degree of freedom of spectrum is typically the most challenging part, yeah, to engineer the photon sources such that this kind of spectral degree of freedoms match. And that's exactly the, so to say, innovative aspect about this research of quantum interfaces, which I will explain at the end of my talk. So now multi-photon interference is essentially this Hongo-Mandel interference on steroids. So there's just more combinations of paths. Yeah? So if you think of 3 photons in some unitary network, and you want to know what is the transition probability, yeah, from the state on the left to the state on the right, then you basically have to add up all these different combinations coherently. Yeah? As you can easily work out, there are 6 of these combinations for the 3 photon state, and in general, if you have n particles, there's n factorial terms which need to be added up coherently, and that's actually quite a lot of terms, and it's so many that for a random unitary, and if the number of modes is large enough that you avoid clustering of the photons, that's basically an exponentially hard problem. Yeah? There's no efficient algorithm to calculate this, and already at a scale of 50 particles, which is of course way beyond what experimentals typically work with, but it's still a reasonably low number in some sense. This becomes infeasible on a classical computer, yeah, and that sets the stage for this boson sampling problem. Yeah, formulating a classically hard problem. So basically, no classical computer can efficiently calculate this. Whereas if you build a quantum machine doing that, well, the machine does that. Yeah, and that can in principle bring you to this quantum advantage regime. And that's with some added ingredients what people have done in this Gaussian boson sampling experiment. Now the problem is, once you have built a machine, how do you know the machine does what you want? Yeah? You cannot just calculate what the machine does anymore. And that's a very fundamental problem, yeah? how to verify the operation of these multi-photon interference devices. And there's different answers to that, and one way to verify that the particles are indistinguishable are so-called suppression laws, so kind of generalizations of this Hongu-Mandel effect. So like certain patterns in the interference which lead to a zero coincidence, yeah, as does this Hom dip. And it turns out if the unitary is not random but has a certain structure, one can often identify classes of states which have a zero output probability for certain events. Yeah? And then you could look for these events and measure their output probability. And if it's zero or close to zero, then you know that you have at least indistinguishable photons to begin with. Yeah? So it's a tool to test the indistinguishability of the photons. And there's a range of these suppression laws which have been known for some time. And typically they work like, okay, I have this and that unitary, and I have this and that symmetry of my input state, then I have a certain class of outputs, yeah, which has a zero probability. Some time ago, my PhD student Christoph Dittel and I kind of could generalize this suppression law, yeah, via some theoretical considerations. We found a more general law, basically where we just start with this input symmetry, so we just need to define a certain symmetry, for example, here a cyclic symmetry of our input state, and that was enough to predict us all unitaries which have some suppression and give us also the set of suppressed output events. So it was somewhat more general, and it contained all previously known cases. And we could also extend it to fermions. We could extend it to entangled input states, and we could also look at what happens if not all particles are indistinguishable, but subsets are. Like the relation to entangled states, that will become important again in the second experiment, which I will talk to you about in 15 minutes or so. And this, what happens when a subset of the particles is indistinguishable, as I will discuss right now. So then we thought of a setup like this. So think of, we have a unitary which has a certain symmetry, for example, like a mirror-like symmetry, yeah, and all particles are indistinguishable. Then we know from these suppression laws that we would have suppression there. So there would be some output states which have zero probability. On the other hand, if all particles are distinguishable, all have different color, yeah, then no suppression would be expected, because the internal degrees of freedom just don't overlap. Now, this kind of new case, yeah, we studied was what happens if only certain subsets of the particles are indistinguishable, which are paired by the symmetry. Doesn't need to be paired, could also be a cyclic symmetry or in groups of 3 or 4, yeah, but in principle, if only subsets of the particles are distinguishable, if the right subsets are distinguishable, the theory predicts there should still be a suppression. Yeah? And as a counterexample, if the wrong pairs of particles are indistinguishable, there should be no suppression because it doesn't match the symmetry. And that's what we tested in an experiment. For the unitary network, we used a waveguide network, which was inscribed by femtosecond laser pulses by our collaborator Alex Zammert in Rostock. So this works as follows. We have waveguides in a photonic chip, yeah, which are brought together in a region where there's evanescent coupling between the waveguides, and the distribution had to follow, or the coupling had to follow a certain distribution with weaker coupling on the outside, where the waveguides are further apart, yeah, and stronger coupling in the center with a certain set of parameters. Then as a photon source, we used parametric down conversion, which most of you probably know, yeah, in case you don't. So down conversion means a pump photon gets converted into a single and idler photon with respecting energy conservation. That means the sum of the frequencies of these single and idler photons must be the same as the pump photon, and also momenta need to be matched. That is the k vectors. Is there a question?
So for the waveguide,
yeah,
you did the symmetry, so you knew that you need something that is symmetric by the middle.
Yeah, exactly.
Sorry, so for the waveguide you need the symmetry, so symmetric by the middle, but did you think of what, because you said it generally that you just consider random.
Yeah, so it's basically...
you call it JX unitary.
Exactly,
so
it's not just any mirror symmetry, it's a particular mirror symmetry. Yeah? So this suppression law for this particular configuration required a certain distribution of these couplings, yeah, which is derived from the eigenvalues of the angular momentum operator.
Okay,
that's why it's called the JX.
So,
yeah.
okay, so your Z will be like Jordan-Wigner, JZ is the standard basis, and X will be like A dagger B plus B.
Yes.
Okay,
yes,
I see,
exactly.
I see. So it's like D Wigner matrix rotation or something. To get
like that. Yeah.
Okay, I see. I see.
So and you just don't need this particular coupling distribution. You also need the right length. Yeah. So the length of these waveguides need to be such that there's a certain chance of each photon going to each output with some modulation.
So for the student, if you treat the photons, they are like spin in Z. You want a rotation in X, or measure the angular momentum in X. And this is what this unitary is implementing.
I think so, yes.
Yes, and it has a symmetry about the middle, spin up, spin down. About X, no?
Yeah, I mean, it's been many years that I thought of the theory of this, so I would need to double check to be sure on that, but it certainly relates to this JX operator.
Okay,
yeah.
I see. Okay, thank you.
All right, so that's, I've used parametric down conversion as a photon source, and we wanted to do a 4-photon experiment in that case. So basically we needed the scenario where 2 of these pump photons get converted, and in principle it was for the exposure type 1 phase matching. That means the photons are always emitted on a cone, yeah, with a certain opening angle, and once in a while you have like 1 pair emitted in the directions A and B here, and 1 pair in the direction C and D, and that's what we collect, yeah, with mirrors and fibers, and that's then our 4-photon source in that experiment, giving a reasonably good indistinguishability for photons from the same pair. Yeah, so if they are these visibilities here, if the photons are created from the same process, they have typically very good indistinguishability. They're not so good if they are created from different pairs. Why that is so, I will explain in the end.
Sorry, what is like operational meaning of those numbers?
What these V's mean?
Yeah.
Yeah, so these are the Hong-Mantel visibilities. So like this visibility of this dip. Yeah, if you measure this Hong-Mantel dip, measuring the indistinguishability of the photons, that's how indistinguishable they are. If it's 100%, it's perfect. Yeah.
Okay, so it's like overlap of internal.
It's the overlap of the internal states. Exactly. Yeah. Yeah. So that's throughout my talk. The V will always be this Hong-Mantel visibility. Yeah, this internal state overlap. And then we take up these photons, send them through optical delay stages that we can tune their temporal delay independently, and then we can adjust these settings of indistinguishability, put them and couple them to this waveguide structure and detect them with photon counters. And then we measure the output statistics, yeah, so which output state gets what relative probability. For example, that particular output state shown here has a certain probability, can be put into a histogram. Yeah? Some other output state has some other probability, just another entry in the histogram. And in that way, we can basically assign a probability to all output events here. We just measured non-collision events. That means events where there's not more than 1 photon per mode because the detectors were non-photon number resolving. Now, for some of these events, yeah, we expect a suppression. That's what this particular suppression law for this particular JX unitary dictates. It dictates that if there's an odd number of particles in even modes, that state should have a 0 probability. So for example, the state here has 1 particle in mode number 2, yeah, and that's the only particle in an even labeled mode. That's why it's a forbidden state, and it should have a 0 probability. It doesn't have precisely 0, due to some experimental imperfections, but it should be low probability. And all the states in this gray region here are the states where a suppression is expected in principle, and one can basically quantify the degree of suppression in this experiment by just summing over all these probabilities of the theoretically forbidden event, which was 30% in our case. And then we extracted this probability for these 4 different configurations of indistinguishability. And one could clearly see that in the case where a suppression is theoretically expected, one has about maybe 30% probability, and it's about 40% in the case where no suppression is expected. So this difference between 40 and 30% is, so to say, our experimental result. And it was a significant result. And the importance of this is that kind of this scenario here of indistinguishability only among subsets of particles, that was not considered before when people thought of using these suppression laws for verification of boson sampling. Yeah, they always thought of, okay, I can just use a suppression law on any unitary and I see that all my particles are indistinguishable. What we showed is one has to be careful. Yeah? One has to pick the right unitary which doesn't have this, so to say, breaking in cycles. So in that sense, one could not use this unitary to certify the indistinguishability of all the particles. You might wonder, okay, why do you just see 30%, a reduction to 30%, yeah, and not to 0? What are your limitations? One big limitation is higher order emission from the source. So once in a while, the source emits 6 photons, and then you see interference of 6 photons and detect 4 out of them, and then this just spoils the statistics, basically. The limited Tongo-Mantel visibility is an issue, and also this unitary has a certain finite fabrication precision.
On the previous slide, you had much lower probabilities.
It was 30% on the previous slide. 30% is the sum of everything in the gray region.
Okay,
yeah. And we take the sum because that should be 0 in theory if suppression was perfect, and then we compare these sums for the 4 cases, yeah, and that's basically what we get. But we understand what's happening. So basically, we have a physical simulation for this.
I wanted to ask. So when you say you impose some, let's say, partial distinguishability structure, so you assume that some photons that they don't, like internal linguists totally don't overlap.
Yeah, exactly. So we really physically delay them in time by so much that the delay is larger than the length of the wave packets.
Okay, but like when you have multi-photon, like distinguishability, like you're gonna probably say about collective phases. So like, do you think that those effects of collective phases, because like so far you just talked about overlaps, not relative phases. Do you think that those?
In that case, I'm pretty sure they didn't matter. Yeah, because this is. I'm trying to revive the laser pointer. This is a pairwise interference effect, and as I will explain in a few slides, when you have interference of pairs of photons, the phase never plays a role. Yeah, but if you have multi-particle interference, then it can play a role. But in that experiment, the collective phase wasn't an issue. It was really just an issue of overlap, and here in that case we really tuned from practically 0 temporal overlap to practically 1 temporal overlap, and then the overlap was just limited by spectral degree of freedom mostly.
So in ideal case, this value here should be 0, right? Because
yes.
So
yes.
The lower the better.
The lower the better. So in the upper case, yeah, you would want to see a 0 here and 0.4 there, more or less, yeah, if everything was perfect. Exactly. Any more questions on this first experiment? Okay, then the question on collective phases is just the right question, yeah, to bring me to this next topic. So let's go back to the Tongo-Mantel interference experiment and quantify a little bit more what means indistinguishability. Yeah? I said it's the overlap of the internal states, yeah, typically spectrum, but also time and everything else. And this overlap is a complex number. Yeah? It has a magnitude and has a phase. The 2 extremes of fully distinguishable, which kind of forms the plateau of the Hom dip, and fully indistinguishable, which is the dip of the Hom dip. Okay, these are the cases r equals 0, r equals 1. That's kind of what we considered so far. But of course, there's this interesting region in between, yeah, where there's a continuum of magnitude of distinguishability. And if one works out the theory, how do you calculate for this beam splitter interference the probability of a coincidence? It turns out you have to take the difference of 2 terms, the difference of the product of these internal states, which is 1, like of the individual products, minus the product of the cross product, so to say, and then you end up with 1 minus r square for this for the 2 photons on the beam splitter. And obviously this does not have any dependence on phase. Yeah, so with 2 photons, this kind of phase of this internal state overlap is completely irrelevant. But for more particles, it's more complex. Interesting things can happen. Yeah, and first, so to say, a demonstration of this effect was done in 2020 in Ian Wormsley's lab. What they looked at is, okay, you have 4 particles in 4 modes in a 4-mode interferometer and measure the coincidences of these 4 particles, and they chose a particular configuration of internal states overlaps, which you can put on this kind of cycle here. Yeah, so kind of all these neighboring particles on the cycle, they have some non-vanishing internal state overlap, and the 2 particles which are opposite on the cycle, they have 0 overlap. Yeah, and they kind of engineered this internal state overlap and showed there is a collective phase interference that is an interference in this 4-fold coincidence probability, which depends on the phase, which is given by the sum of these 4 internal state overlaps, which is, so to say, a ring phase, a cyclic phase up there. And then, yeah, you see a nice interference pattern there, and it's a so-called genuine 4-particle interference, because all the lower orders, for example, 3-fold coincidences, they are essentially flat. Yeah, you don't detect this interference pattern if you break the cycle. You have to measure the interference of all 4 particles in the cycle to see it. One issue with that interference, however, is that for n particles, you need an n-dimensional state space, internal state space, to engineer it. So you cannot simply take polarization, for example, but you have to do some clever tricks of time and polarization to get to this 4-dimensional state space, which they needed for the 4 particles. And the contrast of this oscillation, it's not 1, not even in theory, and it asymptotically decreases if you have more particles. So it becomes, so to say, harder and harder to detect, yeah, if you have more particles. And together with our collaborators in Freiburg and at Heriot-Watt, we thought of a new experiment where we want to use entanglement as a resource to engineer a collective phase. And in particular, we thought of this experiment. So we have now 2 beam splitters and 4 particles. 1 pair of particles is entangled in this kind of bell.
Should work now.
Okay, thanks a lot. So we have kind of 1 entangled state, and 2 particles were in a separable state. That was a superposition state of the 2 basis states, yeah, a balanced superposition of the 2 basis states with some internal phase phi and theta. And then one can show that again the 4-particle coincidence will have a interference which depends on the collective phase, that is essentially the sum of these 3 phase terms, chi, phi, and theta. It's also a genuine 4-particle interference, because all the lower orders, like singles, 2-folds, and 3-folds, would show a completely flat line. Yeah? So you need to detect all 4 particles to measure this collective phase interference. And in contrast to the collective phase interference discussed on the previous slides, it just needs a 2-dimensional state space, which is nice for us photonics people, so you can use polarization states, for example. And the contrast remains 1, yeah, independently of the number of particles. So the interference pattern always goes down to 0 for an arbitrary number of particles. And then we wanted to demonstrate this in an experiment. So we need some single photon source, get 4 copies of ideally indistinguishable photons, entangle 2 of the photons, and then encode this superposition states on the 2 other photons. Again, we use down conversion. two SPDC sources in parallel. In this case, it was collinear sources. For the entanglement, we use the Sagnac interferometer. So the idea of a Sagnac interferometer is the pump laser enters with diagonal polarization, so it's split and it enters here on the PBS. So it's split into a fraction of pump light going counterclockwise through the interferometer and a fraction of pump light going clockwise through the interferometer. And then down conversion can happen in both directions. Yeah? And you get at the output a state which is a Bell state given by the interference of clockwise down conversion and counterclockwise down conversion in this Sagnac interferometer. And the good thing is the fidelity of this Bell state then just depends on the indistinguishability of the rotation direction in the Sagnac loops, which is typically very robust, yeah, to any kind of experimental imperfection which you might have in your system. And for encoding these kind of internal phases of the single photons, we just used some wave plates and rotated the half wave plate to set the phase of this polarization superposition state here. That's then how the whole experiment looked like. So the two sources, one entangled pair and the other pair, the non-entangled pair, put on the beam splitters, changing the collective phase and detecting the photons with single photon detectors. In that case, it was at infrared wavelengths where sources are better. So in that case, we could use a source which has about 98% homomandel visibility. And also the Bell state fidelity was very good. These are the experimentally recorded collective phase interference traces. Believe me, the lower orders, 3-folds, 2-folds, they are essentially flat. Yeah, so it's really a genuine 4-particle interference effect. The dominant, let's say, limitation of the visibility in our case was one thing was like a certain drift in the pump laser power over time, which kind of degraded our visibility, and again the higher order emissions from multi-pairs. That brings me to the next topic. Yeah, so this higher order emission, that seems to be a consistent problem. Yeah, when you use down conversion for multi-photon experiments, and I want to explain you in more detail why it is a problem. Yeah, so down conversion is a probabilistic process. So you can think of a laser pulse having many pump photons, and each pump photon has a certain probability of being converted. So once in a while, you don't just get one pair, but you get 2 pairs emitted into your collection modes, or even 3. And in principle, this probability to get n pairs scales essentially polynomially, yeah, with some parameter p. And you can, which essentially depends on the pump power you're using. So you could use little pump power, have this p very small, and then you have the statistics as you see it here on the left. So most of the time you generate nothing, and once in a while 1 pair, and then the probability of more pairs is very little. So it would be then a source which is clean in the sense that you get a controlled number of emissions, but most of the time you get nothing, so it's not a very bright source. Or you crank up the pump power, then you get more pairs, but also more multi-pairs. So you have a brighter source, but a less cleaner source. And this kind of intrinsic trade-off, yeah, between brightness and single photon character that you can never avoid with these down conversion sources. You always have it, which is why there's a lot of interest in working with single quantum emitters as light sources. So if you think of a 2-level system with a ground and excited state, this can naturally just emit a single photon at a time, yeah, because you can just excite it once to the excited state. And we are using semiconductor quantum dots as single photon emitters also for our experiments. So for those of you who don't know what a semiconductor quantum dot is, you certainly know that in a semiconductor you have a valence band and a conduction band with a certain band gap. If you now bring 2 different semiconductors close together in a so-called heterojunction, you have then 2 different band gaps next to each other. Yeah? And if you sandwich the low band gap material with the high band gap material in all 3 directions, you end up with a quantum dot, yeah, which is really a three-dimensionally confined system for the electrons and for the holes. And as you know from quantum mechanics, when you have a quantum well, you get discrete energy levels in this quantum well, and that's exactly what you have in the quantum dot. And moreover, these electrons and holes in the quantum dot, they have a charge, so they interact and they can form bound states, a bit like a hydrogen atom. Yeah, and these bound electron-hole pairs, they are called excitons. And those are the fundamental excitations in this quantum dot. And then the idea is we take an empty quantum dot, send in a laser to excite it, to create one exciton, and then you wait for spontaneous emission via the decay of these excitons. We get our quantum dots from our collaborator Armando Rastelli in Linz. So they are gallium arsenide quantum dots surrounded by aluminium gallium arsenide. They are typically on the 50 times 10 nanometer scale, and they are emit at near infrared wavelengths. One issue in working with quantum dots is that the semiconductor materials have typically a tremendously high refractive index, so it's not so easy to actually extract the photons from the semiconductor, due to refraction at the interface. You just have a very, very narrow cone of emission towards the surface, which makes it out of your device into some optical mode you can then collect. One can improve that by putting cavities around it. In our case, it was a planar Bragg stack, so Bragg mirrors below and above, which kind of funnel the emission more due to interference, bringing this kind of extraction efficiency up by 1 order of magnitude. And then these quantum dots, they need to be operated at low temperature, because at room temperature there would be too much phonon noise, the transitions wouldn't have a nice line profile and so on. So that's why we operate them in closed cycle cryostats typically. And one challenge is, of course, that if you use a direct resonant excitation, that is, the laser is directly at this transition line, then it's not totally trivial to separate the emitted photon from scattered light of your exciting laser because they're at the same wavelength. And what we typically use is this polarization extinction. That is, we send in the laser light at a polarization which is at a superposition of the two natural emission directions of the dots, so that the natural dipole orientations. These dots are slightly anisotropic. They have like two dipole directions which they tend to emit. And if you excite both of your dipoles and then collect the polarization which is orthogonal to the excitation direction, then you kind of suppress the scattered laser light via this polarization extinction, and you collect at least half of your emitted photons. When you measure the spectrum, you get a nice line of the emitted photons. In that case, it's 799 nanometers. One can measure what is known as the intensity autocorrelation in this Henbury-Brown-Twiss setup. So there you see kind of autocorrelation peaks every 30 nanoseconds, which is the repetition rate of the laser, which we're used to excite it, but a much lower peak. Note that it's a logarithmic scale here. At the center, which means it's very rare that two photons are emitted at the same time from the quantum dot. Exactly. So it's a good single photon source. Now we have this kind of stream of photons, and for interference experiments, typically one wants to demultiplex them into spatial modes. We want somehow deterministically route this kind of stream of incoming photons into the spatial modes. This should be done as efficiently as possible because essentially the overall efficiency will scale exponentially with this single particle routing efficiency. And how we did this was by putting an electro-optic modulator in, which rotates the polarization of every second photon, so at half the repetition rate of the excitation laser. And then one can split it with a polarizing beam splitter in two modes. And then one has another layer of electro-optic modulators, which again flips the polarization of every second photon, which requires now half the frequency, such that we then have the photons in 4 separate spatial modes. Then you just need to rotate the polarizations to get all polarizations the same and send the photons into fiber delays of different lengths, which matches the temporal spacing of the photons. And then at the output, you get 4 photons at the same time with the same polarization. So we built a setup with, I guess, a reasonable fiber-to-fiber coupling efficiency of 84%. There was a bit of a additional loss you get from routing errors. So sometimes due to finite contrast of the polarization extinction of the PBSs, some photons end up in the wrong channel. That gives you essentially another loss factor, such that we have a total efficiency of about 80%.
Can And emission is no problem, like the efficiency of the emission.
In that case, it was the problem, yeah, because the quantum dots, they were emitting with an efficiency like fiber coupled detection efficiency of about 1%. So you get maybe 10% of the photons out of the quantum dot, but then you have some more downstream losses to make it into the fiber and so on. And then 1% to the power of 4 is, horribly low. And that's why essentially the fourfold rate which we could use in the experiment was, as I wrote here, about 0.17 hertz, which is 2 orders of magnitude less than what we have in this down conversion source, which is why practically we cannot use that source for a 4-photon experiment, but that's not limited by this demultiplexer. That works really nice, but limited by the brightness of the quantum dot source. But in principle, there are brighter sources available. Yeah. So the
laser is 30 megahertz.
76 megahertz, the rep rate of the laser, yeah, and then essentially lose 2 orders of magnitude for each photon, and then a little more from the demultiplexer, and then you end up with this rate. And back at the time when we published it, we made a comparison, yeah, of all the demultiplexing systems which had been published before, and our system was the first, which was fast enough to really route every photon from one channel to the next, yeah, so to keep up with the 76 megahertz repetition rate and efficient at the same time, which I guess was a technical achievement at the time.
So this overall efficiency is not really competitive to SPDC.
I wouldn't say that generally, yeah, so because if you take the best commercial quantum dot systems, they can emit single photons, I think, at a 10 to 20 megahertz rate, so maybe efficiency of 25% or so, fiber coupled efficiency. And if you combine it then with our demultiplexer or a similar demultiplexer, I think then one is certainly competitive with SPDC in rate. Yeah, I think that's doable. With indistinguishability, it's maybe a bit more of a challenge to reach this kind of 98% level, which I showed in this collective phase experiment, but let's say 90 to 95% is also doable. That's why people in principle still work with both, yeah? Both approaches are competitive in a sense, yeah. Good, and then in the final minutes, I would speak about this kind of new topic, yeah, which we are working on with Michael now, about quantum interfaces. So it's actually the perfect question to leading to this topic, yeah. So basically both types of sources are relevant still, yeah. So why not build an interface between the two sources such that both sources can be used together in some protocol and some experiment, yeah. And the wider motivation for this is quantum networks. Yeah, the idea of a quantum network is to distribute some quantum information processing task on different nodes, could be some atoms in separate cavities or so, and transmit photons between these nodes. Yeah. In order for this to work, of course, the photons emitted and absorbed by these nodes need to spectrally match. Yeah, they need to be at really the same color, otherwise it wouldn't work. Or if you think of quantum repeaters, yeah, in quantum communication protocols, there you want to distribute entanglement over a long link. Yeah, you also need to send out entangled states from these quantum memories here and do Bell state measurements in between these nodes. And a Bell state measurement is essentially also or requires also indistinguishability, yeah, because you want to record some coincidences after the beam splitter and so on, and the underlying interference only works if the photons are indistinguishable. So same thing again, the photons emitted by these different nodes need to match. So basically there are two options. Either one has a common standard across the globe that everyone uses the same technology in your nodes, yeah, and they emit the same photons, or we need some clever ways to engineer the spectral shapes of the photons and the frequencies of the photons emitted by different nodes. Yeah? And one kind of maybe inspiring experiment which shows that this kind of spectral matching is impossible for very dissimilar sources in principle is this one here, where they took photons emitted by the sun and photons emitted by a quantum dot source and made them homomantle interfere on the beam splitter. As you could imagine, yeah, the spectral bandwidths are vastly different. Yeah? So like a gigahertz bandwidth at the quantum dot and yeah, super broad from solar light. And what they did was essentially very rough or very tight spectral filtering. Yeah? So basically most of the solar photons are just filtered out. And then in principle one can do it. Yeah? In our case, we don't have to bridge so many orders of magnitude. Yeah, we just want to bridge roughly.
What was the visibility?
I think it was quite good. I don't know for sure, but I think it was just the key was this tight filtering. Yeah, so they filtered to this essentially to the narrow line width of the quantum dot and some stabilization, and then they got a decent visibility. Yeah, just not efficient. Yeah, but there's a lot of solar radiation, so that's why it worked. So in our case, we just have to bridge 3 orders of magnitude in bandwidth roughly from the kind of SPDC source I've shown you in the first experiment and the typical quantum dots, which is, you know, not as extreme as with solar light, but enough of a challenge to write a project proposal and get it awarded. Yeah. Our goal is basically to set up an experiment which looks like this. Yeah? So we take photons from down conversion and photons from a quantum dot. Both are pumped by the same pump laser for synchronization. And the most straightforward way to spectrally match them would again be filtering. Yeah? So just putting a tight spectral filter in the SPDC path and then measuring coincidences at the beam splitter. So people have done that in the past with this passive filtering, works, but of course it's very lossy because you throw away most of your down conversion photons. Instead, we want to follow kind of a hybrid approach. We want to do some moderate filtering to about 100 gigahertz bandwidth of the SPDC photons, and at the same time do spectral expansion of the quantum dot photons in the so-called time lens, with the hope that this is more efficient, with many reasons to think that this is more efficient than the passive filtering alone. Probably you have heard how the time lens works. I will just explain you very briefly here. So the idea is to take a pulse of light, put it through some dispersive elements such that you get chirp on this pulse, and then use a temporal modulation in electro-optic modulator. So another quadratic phase, and if the curvature of this quadratic phase in time matches the quadratic phase in spectrum from the dispersion, the chirp cancels out and you get spectral compression in that case. And this is analogous to diffraction at the lens, due to paraxial diffraction, where the dispersion corresponds to the propagation in free space, and you apply a quadratic phase in kx, so in transverse momentum, and the lens is a phase in x, which is analogous to a phase in time in the spectral compression. And in our case, we would do spectral expansion, so we would go from right to left, having the modulator first, and then the group delay dispersion. So for time reasons, I will skip the outlook and go to the conclusion right away. Just turn this off. So I basically gave you a summary or introduction to multi-particle interference, showed you that one can generalize this Hong-Mandel effect to suppression laws. I linked it to symmetries and showed that the symmetry of the input state is really important, and one has these kind of pairwise indistinguishability scenarios, which is more subtle than this full indistinguishability considered before. For 3 particles or more, one also has to take care of the phase of this internal state overlap, which can lead to this collective phase interference effects. When using quantum dot sources for such experiments, it's important to have a demultiplexer, and I showed you one. And finally, we work on interfaces via active spectral conversion of quantum dot photons. And I didn't speak about the outlook, but we also work on some bringing this visibility of 98%, which was the visibility we got in this collective phase interference experiment, even higher. And the limiting factor there is the spectral shape of the pump laser. So if the pump laser gets a nice Gaussian profile, one can in principle bring this higher up, and that's one of our current works. Let me thank my team, my team of students. You did most of the work, and Gregor, who hosts the group, also previous students, collaborators, funders, and thank you for your attention.
Thank you very much. Questions? And maybe you
can repeat the question.
Yes, sure.
You can use this one.
Or
Okay. So,
you don't
yeah,
need to repeat.
now it works. Okay, so can you? I don't know if you know, but regarding your competition, like this PsiQuantum, so what they actually use?
They're not my competition, you know. I'm an academic. I cannot compete with them clearly.
Yes,
That's
but
not
so do you know what actually photon sources they use?
Yes, so they have on-chip ring resonators. So they use I think not SPDCs, but spontaneous four-wave mixing. So it's a third order nonlinear process, but in principle, same idea. You can generate pairs of signal in idler, and then you have many of these rings in parallel, so producing multiple signal idler pairs, and some clever engineering then also to make the spectra of these signal and idler photons indistinguishable, such that many of them can be used. Yeah.
They don't do quantum dots.
No, not yet. I mean, they say they are thinking about it, but not yet. Which is obviously with quantum dots, you always have the problem. You need cryogenic cooling of your source, yeah, on the same chip, and it's certainly an added complexity. Yeah.
Yes, so I had one thing I didn't understand. For the collective phase, you said you created Bell states for the middle ones to 98%.
Yeah.
But these fidelities you estimated from, or you did a first experiment to just do tomography?
No,
or
exactly. We did a separate tomography
Okay.
on the
Okay, I
states.
see.
I
Okay.
might have the slide on this. Just check it.
I see. Because if you just use the data
No,
for
obviously
photons,
not
you have multi-clicks and okay.
Exactly. The data is of course affected by many other things. Yeah,
I see. Okay, then I
don't have the tomography matrices here, but it was done by separate quantum state.
Okay.
tomography,
But
yeah.
then, and the second question is a follow-up on Rafael. So what is, so I'm not an expert, but I understand for quantum dots, there's the CNAR, what they call Quandela type of sources.
Yeah.
So I understood that your type of quantum dots are actually their advantages. They are driven by laser, no?
The Candela dots can also be driven by laser.
So somehow, okay, if you can sum up, because the efficiency is lower.
Yeah. So no, what really?
What is the advantage? Because from your proposal with Michał, I see that it's nicely. You could drive SPDC and your dot with the same laser, which probably
Exactly. So that's one big advantage. So they work at 800 nanometers, which is you know kind of a commonly used wavelength and so on. That's one thing. Yeah. And they are also a little faster in their emission. Yeah. So the slide is. So these gallium arsenide dots. Yeah. So the typical lifetime of the excited state there is about 150 picoseconds or so, where it tends to be a little longer on the indium gallium arsenides, which are the one which are used by Quandela. So in principle, one can drive them a little faster. Yeah. And the main limiting factor for the extraction efficiency is really this cavity. Yeah? This cavity is only planar, and there's no transverse confinement of the emitted photons. And what all the advanced sources do, they have a strong transverse confinement of the light, and then you reach extraction efficiencies not of, let's say, 12%, but of 50, 60, 70%, and so on. And I think there's one work where this has been done also with that type of quantum dot, with the gallium arsenide dot.
So it's like putting it in a waveguide kind of.
Here, I think so. They put like a circular Bragg grating on this chip, which contains the gallium arsenide dot, and then they measured even 85% extraction efficiency. The problem there is only it's kind of hard to fabricate and to get the positioning of this grating right over your dot. That's really hard. So I think they tried hard and got one out of, I don't know, 100 or so.
And the driving laser is similar?
Driving laser is similar, so you can still use direct resonant excitation with this. Just everything is harder. Fabrication is harder. Also, the controlled excitation to get the location of your exciting laser right, the polarization right. That's all a bit more challenging. But in principle, it can be solved also for these dots. Yeah.
Thank you for a nice talk. I have two questions. One very quick one, like how do you estimate like purity of internal degrees of freedom in those experiments, and what is it?
Yeah. So for this, there are two ways to do it. Yeah. Okay. I should maybe go back. Yeah. Maybe a little more. So the important parameter is the so-called spectral purity. So I had no time to talk about this. This would have been part of my outlook, actually. But one can, or maybe I put up one outlook slide. That should be fair enough to do. Yes. Okay, maybe that slide. So kind of basic problem in down conversion sources is, you need to engineer the spectral, the joint spectral density, which is the two-dimensional probability distribution of these two frequencies of signal and idler photon, to be round. Ideally, you want here a nice round Gaussian shape, and then there's no spectral correlation between signal and idler photon, and then in theory you would get also perfect spectral overlap of a signal photon emitted by one source and a signal photon emitted by another source. That's this kind of different pair homomantle interference. And then we can measure this by essentially time of flight spectroscopy. The idea there is you send the two photons which were emitted over a long fiber or some dispersive element, which kind of delays different colors differently, and then you measure with your SNSPDs, with your detectors and your time taker, you measure a two-dimensional time correlation histogram, and this you can calculate back to wavelength, and in that way you can measure a two-dimensional wavelength distribution, and from this you can calculate the spectral purity of your photons. But that also only gives you, so to say, an upper limit. The best case, if everything else is perfect, then that would be the homomantle visibility you have. And then you can measure the homomantle visibility, which gives you basically the overlap of all your internal degrees of freedom combined, including polarization and so on.
Thanks. And okay, second question is about this genuine like n-body interference. So you like you gave an example of the paper by Wamsley and others. That they crafted this arrangement of internal states. So yes, okay, you're like how to put it? Okay, I'm like familiar that in the generic case when you have internal states, if they all, let's say, overlap with each other, so they are not orthogonal, just like sort of three body phases would be like enough to. Yeah, exactly.
There's also a precursor experiment where they did three body phases.
I wonder what is like operationally, what is genuine, like how to put it, like
how the word genuine is defined in that sense.
Like
sure. So what we and others normally mean by this is if it's a genuine 4-particle interference, let's say, you should see no trace of the interference if you detect less than 4 particles. So like if you detect just subsets of 3 particles, you should see a flat signal, which is basically this flat signal which they saw here and which also we saw in our data. And same goes basically for a 3-body phase or 3-particle interference. If you don't see any interference just by looking at pairs individually, then it's a genuine effect in that sense.
Okay,
that's how it's meant.
Okay. Final quick question. Is there a final quick question? Okay, I don't see any further questions, so let's thank our speaker again.
Thank you very much.
There will be no seminar next week because we'll be celebrating the Labor Day. There will be no seminar in 2 weeks, I believe. Yes, because of, or is this not true? That's what our spreadsheet says, Rafa. So it's like there will be no seminar in 2 weeks because this is the quantum conference in Gdańsk. So the next seminar is in 3 weeks, and we'll have a guest from Madrid, whose name I already forgot. Alvaro from Madrid. Thank you very much. Robert is here until tomorrow, and we'll be going for lunch now.